Hello, everyone. Good afternoon. Good to see you all. Thank you for turning on your cameras. I love to be able to see you and your reactions. So that is just great. I appreciate it. Just another reminder about the evaluations. If you haven't done those yet, I think now about 25% of you have done them. So there's still 75% to go. You might have done another evaluation for this class for a different instructor. But only 25% of you have done it for me. So I need you to do those evaluations. Please try to do that. You should have gotten some emails about it. You can also just go to our homepage on Canvas. On the bottom left, there's a little block for student evaluation of instructor. Click on that and you can do the evaluation for this class, okay? That would mean a lot to me if you can get to that in the next couple of days. I would really appreciate it. So at the end of last time, if you remember, we were kind of in the middle of quantum mechanics, or actually not the middle, we had just introduced quantum mechanics. And so that's our topic for today. We're going to continue on that path. You watched a video today, a couple of videos on light and quantum mechanics. So hopefully those made sense. But before I get going, as always, I wanted to see if there's any questions on anything. If you have a question, use the raise hand function in Zoom and I'll call on you. Okay, looks like no questions. So, oh, Alex, got a question.
Yeah, so.
Always reliable for a question, Alex.
Huh?
You're always reliable for a question, so thank you.
Yeah.
Go ahead.
I just wanted to point out when you mentioned the instructor evaluation. So I sent what I think is my second one, but when I click on the link on the Canvas page, it only shows it for one specific course. So
Okay,
I don't know why that is.
Does it mean that you've already done it for this class? I'm not sure. What does everyone else see? Anybody else see something on the Canvas course when they click on that?
Honestly, for me, I keep clicking on it and nothing shows up. So that's why I haven't done it.
What was the question again?
Pardon me?
What was the question again?
About the instructor evaluation tab on the Canvas homepage. Has anybody been able to get that to work?
I wasn't able to click on that one. I had to actually wait until I received it through email.
Okay.
Because even now, after I did the evaluation, I try to click on it on Canvas and it doesn't open. It stays blank.
Okay. I don't know what the deal is with Canvas, or maybe that's not working, but you should have gotten an email for this class, and probably more than one, because you got one for your lab instructor and one for me. So if you can just go back through your email, they'll probably send you another reminder as well. But if you just go back through your email and find that one, click on it and do that evaluation.
I did the evaluation and it worked fine for me.
It worked fine for you on the Canvas page?
Yeah, I did the evaluation, yeah.
Oh, okay. Okay, great.
Right, okay, right after I finish my one evaluation, it takes me to like a completed page that it shows like the different available ones that need to be done. But I just wait for another email to come in that says I need to do another one instead of just.
It works off the email, and you should be getting emails about it. So if you get another email about an evaluation from me, I'd really appreciate it if you took the few minutes. It doesn't take very long to fill it out. Okay. All right, let's jump in here. So this is actually one of my favorite topics. Part of the work I did as a postdoc at UC Berkeley was making very, very short pulses of light and to measure chemical processes that happen in very, very short periods of time, like 10 to the minus 12 seconds. And when you make these really short pulses of time, you run right into the uncertainty principle, which is at the heart of quantum mechanics. So we're going there. We're going to try to understand that today. I'm going to try to explain to you an experiment called the double slit experiment. You saw a version of it in the video, but we'll go into it some more today. And hopefully by the end of today, you'll understand that, okay? At least you'll understand the heart of quantum mechanics, because the double slit experiment contains within it, right, the very heart of quantum mechanics and what it means for a particle to have wave properties and for a wave to have particle properties, okay? So that's what we're going to jump into. But first, we got to finish a little bit about light. So remember, last time we were talking about light, which is electromagnetic radiation, right? We talked about its wave nature. Because light is a wave, it undergoes interference and diffraction, which we have to understand those things in order to really understand the double slit experiment. So what is interference? When two waves meet or interact in ways with their troughs, and their crests aligned, they'll add together and make a wave twice as big. This is called constructive interference. You might have seen this on the breakwater. How many of you ever walked out on the breakwater and watched the waves out there? When a wave comes in and hits the breakwater, it bounces back. And sometimes it'll meet another incoming wave. And when the two incoming waves meet, boosh, it shoots way up, right? That's constructive interference, okay? That's because crest and crest have aligned and boom, you get a wave twice the size, okay? If waves meet in such a way that a crest and a trough align, then they destroy each other, and that's called destructive interference, all right? So when waves add together this way, they actually cancel each other out. This way, they multiply together, and this way, they cancel each other out. Okay, that's called constructive and destructive interference. And it just depends on whether or not it's crest to crest or crest to trough alignment, all right? Taylor, quick question.
Yeah, if there's 3 waves, would it be 3 times the size?
Yes,
Or-
yep.
Okay.
Yep.
Okay, cool.
Yeah,
All
they
right.
would all add together, absolutely. So waves also undergo, so that's interference. Waves also undergo a phenomenon called diffraction, all right? And the diffraction of a wave, it's its ability to curve around an obstacle, okay? Let's see, how many of you have ever gone down to Rincon and watched the waves there? This is Rincon Point, right? South of Carpinteria. See some hands up. Gone down there and watched the waves. It's a world-class surf spot for those of you that surf. Also gets very crowded, unfortunately. But what you can do if you're up on the cliffs, you can see the waves come in and you can see them bend around the point, all right? And that's what produces that beautiful, long, perfect right, yeah? And that's diffraction. Waves bend around objects, right? So if you have a wave and it hits a divider like this with a small hole in it, it'll diffract around and you'll get wave intensity over here, right? Even though the divider stops here and here, okay? So waves have this ability to diffract. Particles don't behave that way, right? When particles go through something like this, you don't get any particles over here, right? You get wave intensity over here, but you don't get particles over here, right? Because particles travel in straight lines. They don't diffract. They don't bend around objects, right? Here is just a little picture of a little bay, and you can see the wave coming in and diffracting, right? And it's coming out. Notice you can even get wave intensity way over here, right? Far away from a straight line. If you just had particles coming through here, right, they would just go straight over this way, but waves have this ability to diffract, okay? So this ends up, you can see both interference and diffraction when you send a wave through 2 slits, all right? When you have a divider like this and you send a wave through 2 slits, each slit, it diffracts through each slit. And when you look at the pattern over here that it forms, you get what's called an interference pattern, all right? And why do you get that interference pattern? Imagine the waves meeting up right here in the middle, right? Notice that the waves would have to travel that path length and this path length, right? What do you notice about those 2 lengths, A and B? What do you notice about them?
They're the same?
They're the same. Perfect. Exactly right. So if you look at 2 waves and they start at the original source, at the same original source, right? And they travel exactly the same distance, how are they going to interfere when they meet?
Constructively?
Constructively, exactly right. So notice right here in the middle, you get a bright spot, right? Because the waves are interfering constructively, all right? Now, what do you notice about these 2 path lengths? This one up here, call that A, and this one down here in the red, call that one B. What do you notice about those 2 path lengths?
They differ.
They're different, right? They're not the same length anymore. In fact, the difference between them is exactly half of a wavelength, right? So if you have two waves and one travels exactly half of a wavelength less than the other one, notice what happens when they meet. Sorry, I didn't draw that super well, but you get the idea what happens. What kind of interference?
Destructive.
Destructive, right? So you see a dark spot right there where the waves cancel each other out. Okay? And then if you go over to here, the difference between the two path lengths is actually an entire wavelength. So when the difference is an entire wavelength, watch what happens. What happens when they meet?
Constructive.
You get
interference.
constructive.
Constructive again, okay? This is called an interference pattern, all right? And it always happens when you send a wave through two closely spaced slits, you get this interference pattern of dark and light spots, okay? So keep that in mind. You can kind of see it here in waves in water, all right? See right here in the middle, you have a high amplitude of wave, and then you have destructive interference. And then you have a high amplitude and then destructive interference again, all right? Kind of see that right there. All right, so keep that in mind. We're going to come back to that in a little bit. The second thing I want to talk about right now, keep in mind that light undergoes interference and diffraction. The other thing about light that was discovered a little bit later was its particle nature. So remember, initially in the late 1800s, electrons were thought to be particles. Light was believed to be waves, right? But then people discovered that light actually exists as particles as well, okay? Light actually exists as particles as well. How did they discover this? They discovered it with something known as the photoelectric effect. Okay, and in the photoelectric effect, what happens is that when a metal, when you shine light on a metal, depending on if you have the right circumstances, the metal will emit electrons. Okay, so metals emit electrons with light. When you shine light on it, it emits an electron. Why? Because the energy from the light gets transmitted to the electron, right? And it kicks the electron off the metal, okay? That is called the photoelectric effect, all right? Now, in order for the electron to be kicked off the metal, the amount of energy that it gets from the light must be greater than the amount of energy that it's bound to the metal, right? So the electron is held to the metal by some amount of energy. In order for the electron to be emitted, the amount of energy that comes from the light must be greater than the binding energy of the electron to the metal. Does that make sense? So light energy must be greater than the binding energy, okay, of the electron. Now, if light was a wave, and only a wave, right, then you would see this effect, and the main driver of whether you would get this or not would be the intensity of the light, right? A more intense light, right, would give you more photoelectrons, and a more dim light would give you less photoelectrons. If you change the wavelength of the light, there wasn't expected to be an effect, because the energy of a wave is proportional to its intensity squared, not really related to its wavelength, all right, from the classical point of view, all right? So what they did expect, they expected a lag time. Low intensity light should have a lag time. What does that mean? That means that if the intensity is too low, it's going to take shining the light on the metal for a little while before it builds up enough energy to kick off the electron. All right. But what they found was that there was no lag time, And the experiment also showed, oddly enough, a threshold frequency. So the experiment showed 1, no lag time even at low intensity light, and 2, a threshold frequency below which no photoelectrons were emitted at all, right? No photoelectrons emitted at all. So it looks something like this. Here you have frequency of light as a function of how many electrons are ejected per unit time, all right? So at low frequency light, it doesn't matter how intense the light was, you wouldn't get any photoelectrons out. That was weird, according to a wave understanding of light. Once you hit this threshold frequency, you'd start, if the light was high enough frequency, right, then you'd get photoelectrons produced, and different intensities would just change the number of photoelectrons. All right. So that was what was observed experimentally. So what happened was then in 1905, Einstein said, aha, the reason this is happening is because light comes in particles. Today we call those photons, right? And Einstein said that the energy of a light particle was equal to h nu. And since nu is equal to c over lambda, we learned that last time, E is equal to h c over lambda. Okay, and what are these things? So E is energy. Of a photon, energy of a light particle. Nu is frequency. Right? Lambda is wavelength. Right? And h was a constant known as Planck's constant, and it's equal to 6.626 times 10 to the minus 34 joules second. Okay, a very small number. All right. But notice what Einstein was saying. Einstein was saying that the thing we used to think about as only a wave phenomena actually is particles. So these, when you have a flashlight, it's actually particles of light streaming out of that flashlight. Okay, and the energy of each particle is proportional to its frequency. The higher the frequency, the higher the energy of that particle. Okay, or it's inversely related to wavelength, right? Because since nu is c over lambda, right, then we know that E is equal to hc over lambda. And so as the wavelength gets shorter, the frequency gets higher and the energy gets higher of each particle. All right. So how did that explain the photoelectric effect? Well, one of these particles had to have enough energy to dislodge the electron. All right. Each particle, each photon had to have enough energy to dislodge the electron. Right. So there was a threshold frequency, right? If that frequency was too low, the energy of the photon was not enough to dislodge the electron, and you saw no photoelectrons. Once you pass that threshold frequency, then the energy was enough and you'd be able to dislodge the electron. Any extra energy would go into the kinetic energy of the electron, right? So as frequency got shorter and as frequency got higher and higher, right? The electrons that were kicked off had more and more kinetic energy, all right? Because the extra energy went to the electron. Now, let's suppose, let me just give you an analogy. So low frequency light would be kind of like throwing ping pong balls at a sheet of glass, right? If you throw ping pong balls at a sheet of glass, does it matter how intense the light is? In other words, does it matter how many ping pong balls you throw? Not really. You can't throw enough ping pong balls to break the glass with a ping pong ball, yeah? Why is that? Because no individual ping pong ball has enough energy to break the glass, okay? But now what if you start throwing baseballs at a plate of glass, right? Then each individual baseball has enough energy to break it, right? So it's the same idea. At high frequency, a single photon has enough energy to dislodge the electron. At low frequency, it doesn't. So that's why you got that threshold frequency. Does that make sense? All right, very good. Here's my baseball, breaking the glass. Okay, so let's just see if we can answer this question really quick. Which wavelength of light has higher energy per photon, red or blue? Really quick, I'll just launch a poll. Red or blue, let's see if you get this. Come on, everyone, vote. All right. Very good. Most of you got the right answer, which is B, blue, right? Why? Because E is equal to HC over lambda, right? As lambda gets shorter, energy gets bigger, right? So which one has the higher energy? The one with the shorter wavelength. So blue light is more energetic than red light per photon. Okay. All right. Very good. Questions? Questions? For the photoelectric effect, Taylor.
So with your analogy with the ping pong balls
Yeah.
and the baseball,
Yeah.
if it doesn't reach the threshold,
frequency.
yes, do they just bounce back, or
Yes.
they just bounce?
They'll just scatter off the metal. They'll just reflect off the metal or scatter off the metal.
Okay.
And the metal might have, they can also, the metal can absorb some of that energy and it'll just turn to heat. It can't, but it won't dislodge an electron.
Okay.
There's not enough energy to dislodge it.
Okay. All right.
Okay.
Thank you.
So then the kinetic energy of the emitted electron is given by this equation. Okay. The kinetic energy is equal to h nu, which is the energy of the photon, minus the binding energy of that electron, right? So notice that the kinetic energy, once you get to a threshold frequency, if you get just to the threshold frequency, right? What is the kinetic energy of the emitted electron? It's essentially zero, right? Right at that threshold frequency, the energy of the photon has enough energy to just remove the electron, right? And the electron doesn't get much kinetic energy. But if h nu becomes much bigger than the binding energy, in other words, if you use a photon that's very, very energetic, right? Then the kinetic energy of the electron is large, right? Because it gets the difference between the two in kinetic energy, okay? All right, so let's do a quick example of the particle nature of light. Let's figure out what is the frequency of radiation required to supply 1 times 10 to the 12 joules of energy from 8.5 times 10 to the 12 photons. All right, so asking for frequency. So we know we're going to use the equation E is equal to h nu, right? And they're giving us, right? They're giving us 1.0 times 10 to the 2 joules of energy. And they're saying that we want that much energy in this many photons, right? And they're asking for what frequency should the light be in order that this many photons has that much energy. Yeah? So we know that this gives us the energy of 1 photon, right? So they're asking what's the frequency, right? That'll give us this amount of energy in this many photons. Well, we got to figure out, okay, how much energy is in 1 photon? So the energy of an individual photon, of this photon that they're asking us to find, right? You take 1.0 times 10 to the 2 joules, and you divide by 8.5 times 10 to the 27 photons, right? And that gives us the energy per photon, 1.17 times 10 to the minus 26 joules, okay? So now this question becomes saying, okay, so what should the frequency be so that the energy of one photon is that? So we go, okay, the energy of one photon is that. We want to know, okay, what frequency should that be? So we just solve that equation for nu. Nu is equal to E over H, right? So that's equal to 1.17 times 10 to the minus 26 joules divided by H, 6.626 times 10 to the minus 34 joules second, right? Our joules cancel, and we're left with units of frequency, 1.8 times 10 to the 7 per second, all right, which is also 1.8 times 10 to the 7 hertz, all right? So that should be the frequency of the photon that we need. If we want the wavelength, we can calculate that from the frequency as well, right? Using nu is equal to C over lambda. Okay, does that make sense? All right, quick question for you. This one's a tricky one. Think about it for a minute. See if you can answer this question. Okay, so let me help you think through this a little bit. So which of these photons has the greatest energy? 325, 455, or 632?
325.
325. Okay, 325 has the greatest energy. So you would expect the 325 nanometer one to produce the photoelectrons with the what? Most kinetic energy or least kinetic energy?
Most.
The most.
Most, right? You'd expect these to produce the photoelectrons with the most kinetic energy, right? Because that photon has the most energy. Which of these wavelengths has the least energy per photon?
632.
632. So if there's one that's not going to have enough energy to produce photoelectrons, which one is it going to be?
Yeah, 632.
632. All right. Does that make sense? So the right, I'm going to go ahead and end the polling here. The right answer is what?
B.
B. Yep. B. Exactly right. Okay. Most of you figured that out. So very good. All right. B is the correct answer. All right, let's move on. So notice what had happened here. Scientists discovered that light came in packets of energy, right? Another way to say that is that light is quantized. That's where the word quantum comes from. A quantum of energy is a packet of energy, all right? So light is quantized, which means it comes in packets of energy, all right? At the beginning of the 1900s, people also discovered something about atomic spectra that also had the same idea that energy was quantized, all right? If you look at light from an element that has electrical current pass through it, you'll see light that looks like this, all right? These are different elements. and this is the light they emit, all right? If you, so helium, neon, different elements, when you pass electrical current through them, they'll emit light of different colors like this. If you look at the light more carefully though, you can find out that it contains specific lines of color, all right? The atomic spectra consists of these lines, right? So if you were to take the line given off by helium or neon or whatever, pass it through a slit, and then separate out by wavelength, what you find are these specific lines at specific wavelengths. And so the question is, why would that happen? All right. So this is just what those spectra look like. See these specific lines. That's very different than a white light spectrum, right, which contains all frequencies of light or all wavelengths, right? These emission spectra from these elements just produce distinct lines at distinct wavelengths. Why? Well, the first attempt at explaining this was the Bohr model for the hydrogen atom, okay? And the Bohr model, again, has this idea in it that energy comes in packets, all right? The Bohr model said that the electron in hydrogen exists in orbits with or specified by a quantum number n. And n can only be 1, 2, 3, etc. It had to be an integer. It had to be an integer number. Okay. And that n determined the energy of that orbit. E sub n was equal to negative 2.18 times 10 to the minus 18 joules times 1 over n squared, right? So you get a picture of the hydrogen atom where the electron can be in this orbit at this distance from the nucleus, which is some energy, all right? Or it could be here, this distance from the nucleus, which is a little bit higher energy, or this distance from the nucleus, which is even higher energy, right? But it can't be in between, right? Notice how this is different than, say, you know, the planets orbiting the sun. You know, the Earth could be a few hundred miles closer to the sun, a few hundred miles further away. Any planet could be really anywhere in the orbit, right? But that's not the way electrons behaved according to the Bohr model. The Bohr model said that electrons could only be in these orbits, okay? So why did we have these line spectra, these spectra that consisted of bright lines at specific wavelengths? Because when you pass electrical current through this element, the electrons would get excited to higher energy orbits, and then they would relax back down. And when they relax back down, they'd give off a quantum of light. And that energy of that light would exactly equal the energy difference between this orbit and that orbit, let's say for this electron, right? Or for this one, it would the energy difference between this orbit and that orbit, right? The energy of the photon was exactly equal to the difference in the energies of the two orbits. Because the orbits had specific energies, therefore the emissions had specific energies and specific wavelengths, right? Again, this idea that energy is quantized, right? That not any energy was available. It's not continuously variable, okay? Came out of this. We'll come back to atomic spectra more completely when we develop a fully quantum mechanical model for the atom. But this was kind of the first attempt at a quantum model, all right? We'll see why this model, though, ultimately had to be rejected, okay? Because this model is not correct, all right? All right, this just shows the energy levels, right? So here's n equal 1, n equal 2. It just shows plots as a function of energy. So typically, again, the electricity would take the electron up to some higher energy level, and then it relaxes back down to a lower one, and it gives off the energy that's the difference between those two energy levels. All right? Okay. Now, so in order to understand the more fully so again, that was just the first attempt at quantizing the energy of the electron in the atom. Again, this model is outdated now. It's not correct. We need a new model, all right? The new model has to take into account the wave nature of electrons, all right? And the double slit experiment helps us to understand the wave nature of electrons, All right. So we're going to do the double. I'm going to walk you through the double slit experiment. You already saw a video on it, right? So hopefully this won't go too quickly for you, but if you have questions, just stop me, okay? And we're going to do the double slit experiment with waves. So we see how waves behave when they go through a double slit. We'll do the double slit experiment with particles. So we see how particles behave. And then we'll do the double slit experiment again with electrons. So we see how electrons behave, okay? So first is waves, all right? What happens if we send waves through two closely spaced slits? First of all, our first observation, and let me just draw this real quick so you can see what I'm talking about. So we have a tray like this. On one end of the tray, we have something bobbing up and down, creating waves. The tray has a solid divider in it, but the divider has two openings. We'll call this opening A and this opening B, okay? And then what we're looking for is what we see over here. What do we observe in terms of wave intensity, right? When it hits this back wall of this trough, okay, of this tray, sorry. That's what we're observing, all right? So the first thing we observe, number one, is that the amplitude of the wave or the intensity of the wave is continuously variable, right? And you know that about waves from seeing them at the beach, right? Waves can be, 6 inches tall, 7 inches tall, a foot tall, 10 feet tall, 10.7 inches tall, right? It's not quantized, right? It's continuously variable. The wave height is continuously variable. And when you observe the wave intensity back here, you notice the same thing, okay? The wave height, when you're talking about waves, is continuously variable. Second thing you observe, if you open hole A and close hole B, you get an intensity pattern that looks like this, PA. So PA would mean that it would look something like that, right? As the waves pass through, right, the greatest intensity would be here, and then the intensity would fall away as you get away from that point, all right? So we'll call this PA. Similarly, if you open hole B and close hole A, you get PB, which looks just like PA, but it's just moved over a little bit so it's in front of the other slit. Okay. So far, so good. Everybody with me? Now, when you open both slits, right? If you open A and B, you get not PA plus PB, but you get an interference pattern as you would expect for a wave, right? You get an interference pattern. The interference pattern would be maximum right here, right? So I'm not going to draw on top of that. I'm just going to move it over a little bit. So it'd have a maximum there, and then you'd have this interference pattern that went out as you moved away, right? So this is the interference pattern if you open both of them. Okay. And why is that? For the very reasons we talked about, right? If they go like this and like this, you get a P because of constructive interference, and then destructive and constructive and destructive and so on. Okay. So far, so good. Does that make sense for waves? Awesome. Okay. Now let's think about the same experiment with particles. All right. So now we have some apparatus, and let's say we're just shooting, let's say you could think of it as a pool table if you want, in 2 dimensions, right? And you're shooting out billiard balls, right? And again, you're detecting, right? You're over here. You're going to observe billiard ball intensity, right? Kind of like you were observing wave intensity before, but now you're going to observe billiard ball intensity, okay? So the first thing you notice, right, is that unlike waves, which have a continuously variable intensity, right, billiard balls are quantized, right? They come in packets of 1. They're not continuously variable, right? You never see a half a billiard ball or a quarter of a billiard ball or a third of a billiard ball, right? You count them 1, 2, 3, 4, right? Billiard balls are particles. They come in packets of 1. They're quantized, okay? Second thing you notice is if you open hole A, you get PA, which looks much like, this is A, this is B, this would be PA, right? Most of the billiard balls would come through and they'd hit here, a few would hit here and here and here, right? But you basically get a pattern that looks like that, all right? And if you open hole B, you get PB, which looks kind of like this, right? PB. That's because the billiard balls are coming through and hitting here and here and here and here, right? And if you open both holes, A and B, you don't get an interference pattern, right? Because these are not waves, right? Instead, you just get PA plus PB. So PA plus PB is going to look something like high intensity here, a little dip, high intensity here, and a little dip. Sorry, that's a terrible drawing, but this is a little bit better, right? You get a bright spot there and a bright spot there. And if you open both holes, there's no interference pattern, right? You just get this beam of particles hitting here and here. Okay? Does that make sense? So far, so good?
So basically with waves, you get a pattern just out of 2 slits.
Right.
With particles, you get as many lines as you have slits, basically.
Correct. Yep.
Okay.
And all these experiments are always going to be only with 2 slits right now, but we're going to look at them individually and then together, right? One open,
Okay.
the other open, and then together.
Okay. All right. I'll keep that in mind.
All right. So now the question is, what happens when you do the double slit experiment with electrons? Okay, what happens when you do the double slit experiment with electrons? So now we're going to set up a device that has a little filament here. A filament boils off electrons, so electrons are being boiled off this filament. You can control how many electrons get boiled off the filament by changing the temperature of the filament. The hotter the filament, the more electrons boil off. The colder the filament, the fewer electrons boil off, okay? And then we're going to have a divider with 2 slits, A and B, right? And then back here, we're going to have an array of electron detectors. All right, a whole bunch of little electron detectors so that we can spatially resolve where the electrons hit, okay? Each of these electron detectors, right, we're going to call this electron detector 0. And let's say we have 1,000 of them. So we're going to call this detector 1,000. And we have everything in between, right? And so we can make a plot of intensity versus detector number, right? So this would be that detector, and this would be that detector, okay? So in other words, these detectors are just going to feed into a computer, and they're going to give us a plot of how many electrons are hitting a detector as a function of the detector number, okay? So for example, if this detector was was getting a lot of electrons, right, we'd see a big bump, say it's here at 200 or whatever, right? Whatever detector number that was, okay? All right, so we turn on the filament to do this experiment. And the first thing we notice, first observation is, just like particles, the electrons are quantized. These detectors, whenever an electron hits them, make a little clicking sound, okay? And then they register on this screen. And what we notice is that when we turn the filament on, these electron detectors start clicking, right? They're clicking because electrons are hitting them. Some are clicking more than others. So some of these are going up very quickly. Some of them are going up more slowly, right? But what we notice is that every click is the same, right? We don't hear a half click or a quarter click, right? We either hear a click or we don't hear a click, right? If we turn down the intensity of the electron gun, what happens? We hear fewer clicks per unit time. But there's no difference between one click and the other, right? What does that remind you of? Billiard balls, right? They come in particles of one. So it's not continuously variable the way a wave was, right? It's quantized just like the billiard balls are, right? Well, great. We kind of think of an electron as particles, so that's how they should behave. All right. We open hole A and we get PA, right? Which means that these guys are clicking a lot and these guys aren't clicking so much. So if we were to plot this, right, it'd be kind of quantized, but we'd get something like that, right? Which means that this, oh, sorry, that's wrong. We'd get something like that, PA, right? We get a lot of clicks for this detector, fewer clicks as we go this way, fewer clicks as we move that way, all right? If we open hole B, we get PB. Here's PB. All right. If we open hole B and close hole A, these detectors are clicking a lot, click, 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 click. But if we move away from there, they're clicking less and less and less, right? We get the same pattern. What does that remind you of so far? Billiard balls or waves, right? They both had kind of that same kind of pattern when you open just one, all right? But when you open A and B, you get the interference pattern. You get, let me move it. This is gonna be hard to see. Right? You get the interference pattern. Sorry, that's a complete mess. I apologize for the design, but you get the idea, right? So in other words, what we expected for electrons was something like this, right? We expect them to behave like particles. But when we actually shot the electron through two slits, what we got was this. They create an interference pattern, okay? So this is a little bit puzzling because on the one hand, they come through as individual particles, but on the other hand, they're forming this interference pattern. So what can be happening? Well, maybe what's happening is that, I don't know, the electron has some sort of wave nature. Perhaps the electron has some sort of wave nature, and an electron leaves the source and another electron leaves the source at the same time, right? So you get two electrons perhaps, and they interfere with each other. Maybe that's happening. So we can make a hypothesis. Two electrons go through and interfere, whatever that means for a particle, with each other. Maybe that's what's happening. Well, we can do an experiment to check if that hypothesis is correct. What we can do is turn down the intensity of this filament, turn it way, way down, so that all you hear is one click every hour. right? So there's hardly any electrons coming off this thing, right? So few that you only have 1 click an hour. If you only hear 1 click an hour, you can be sure that you only have 1 electron in this apparatus at a time, right? And if our hypothesis is correct, and we turn down the electron gun so that we only see 1 click an hour, what should happen to our pattern? What should happen to our interference pattern? You following me? If I turn it down so that there's only 1 electron going through at a time, all right?
It would act more like a particle instead of a wave.
Exactly. Well, if
Well,
our
I-
hypothesis is correct that
ideally.
it took 2 electrons going through at a time to create the interference pattern, right?
Yeah.
Then we'd expect the interference pattern to disappear, right? In
Yeah.
other words, if we only have 1 electron going through here at a time, and it takes 2 to make the interference pattern, then the interference pattern should go away.
Yeah.
Yeah?
Mhm.
So we try that experiment. We turn down the intensity of this filament to really, really low, 1 click an hour. And then we just keep track of the clicks for a month, right? Graduate students do this sort of thing, right? You have a graduate student there and they're just sitting there watching where it clicks and writing it down, and they sit there for an entire month, right? And guess what? What pattern do they see?
They see the same exact pattern.
They see the same exact pattern. They still see the interference pattern, okay? So in other words, what's happening is that a single electron is going through both slits and interfering with itself, okay? That's the only conclusion that we can come to. The single electron is going through both slits and interfering with itself, because even if you have 1 electron going through at a time, you still get the interference pattern. So then you think, oh, shoot, okay, well, maybe the electron breaks in half, goes through both slits, and then interferes with itself. So you say, okay, how can I detect that? How can I test for that? Well, you could put a laser on the other side of the slits. And it turns out when an electron crosses a laser beam, it'll scatter a photon of light, which means it'll produce a little flash. All right. So in other words, if you had a laser here, an electron went through this slit, you'd see a flash from right here. If the electron went through this slit, you'd see a flash from right here, right? So if the electron is breaking in 2 and going through both slits, then what do you expect? A double flash at the same time, right? So you say, okay, great, I'm going to catch this electron doing its thing. You do the experiment, you still keep the electron gun low, so they only hear 1 click an hour. You keep track of where the electrons land and you turn the laser on. Sure enough, every time you hear a click from the electron detector, you see a flash from the laser. You go, aha. Except that the flash is only from slit A or from slit B, never from both at once. All right? It's either from A or B, never from both at once. And if you keep track of a lot of electrons with the laser on, you get this pattern. The interference pattern goes away. When you turn the laser on, the electron behaves just like a what?
Particle?
A
Particle, exactly right. With the laser on, it behaves just like a particle. It goes through 1 slit only at a time, and it creates PA plus PB, right? It doesn't create an interference pattern. Turn the laser off, you get the interference pattern back. And here's the crazy thing. You might think, okay, well, maybe the laser is disturbing the electron somehow, right? What if you turn the laser way, way down to a very, very low intensity? Initially, no change. As you continue to turn the laser intensity lower and lower, eventually you hear a click, but you don't see a flash. What happened? The electron got through without being detected by the laser because the laser intensity was too low. Okay? So at a low enough laser intensity, some electrons get detected by the laser, some don't. The ones that get detected by the laser produce this pattern. The ones that don't get detected by the laser produce this pattern. Okay? And there's nothing you can do about that. That's just the way it is. Okay? So what's happening? Well, the undetected electron acts as a wave and goes through both slits, and it produces the interference pattern. Okay? The detected electron acts as a particle and goes through only one slit, and you don't get any interference pattern. So remember how I said that from Schrodinger's cat, quantum systems can be in two states at one time, right? So when the electron is going through both slits, it's in two states at one time. It's in the state of going through hole A and the state of going through hole B at one time. Kind of like our cat was in the state of being both dead and undead, right? Remember that in Schrodinger's cat? When you turn the laser on and observe it, that's kind of like opening the box. When you observe it, you force it into one of the two states, either the state of going through hole A or the state of going through hole B. Okay. The weird thing is you can't detect it in both states at once. You can't see the cat both dead and alive, right? When it's undetected, it can go through both. When it's detected, it goes through only one. I see a question, Abe.
Yeah, I was gonna. Are you sure it's because you're detecting it that you get the interference pattern, or is it because the scientists observing it have telekinetic powers?
Right. I think it's the telekinetic powers.
All right.
No, it's the observation that changes it. Okay. And what happens is that basically, here's the explanation. So, 4 important principles to take out of this. The first one is something called the uncertainty principle.
Mr. Short, could you go back to the previous piece of paper for just a second?
Yeah.
Thank you.
So the uncertainty principle says that the particle has the electron has a particle nature. What's the particle nature? The particle nature is this, right? When it goes through one slit and only one slit, and it produces a bright spot, right? It has a particle nature and it has a wave nature, okay? What the uncertainty principle says is that you'll never see both of these at the same time, all right? The uncertainty principle says you'll either see it as a particle or as a wave. You won't see both. So when you're seeing this, you're seeing the particle, you're seeing the wave nature. When you see this, you're seeing the particle nature. You can't figure out which hole it's going through and get the interference pattern. All right? Now, the particle nature of the electron is associated with its position, which we call x. The wave nature of the electron is associated with its velocity. More correctly, it's momentum, but we won't worry about that right now. V. All right? Remember what we said we needed in order to get a trajectory when we started talking about this on Monday, right? In order to have a trajectory for a particle, what do we need to know at the same time? Position and velocity, right? If you want to catch a baseball in the outfield, you got to know where it is and how fast it's going and in what direction it's going, right? You got to know the position and the momentum of the position and the velocity, okay? If you don't have both, you can't have a trajectory, right? The uncertainty principle says that these properties are complementary. Complementary properties. These are properties that exclude one another. The more you know about one, the more you know about the other. So the uncertainty principle can be stated mathematically like this. Delta x m delta v is greater than or equal to h over 4 pi. Okay, and delta x is the uncertainty in the position. M is the momentum. Is the mass of the particle. Delta v is the uncertainty in the velocity. Okay. H is the same constant we talked about before, Planck's constant, and then over 4 pi. So notice, for a baseball flying through the air, right, you can know its exact position and its exact velocity. In other words, for a baseball, you can have delta x times delta v equals 0, okay? But for electrons, well, actually, even for baseballs, this applies, but this number is so small that it doesn't really matter for baseballs, okay? But for electrons, which are very, very small, this number is very significant. So you can't have a 0 uncertainty in position and a 0 uncertainty in velocity. Those multiplied together got to be greater than or equal to some value, right? And why is that? Because you can't see the particle nature and the wave nature at the same time. All right? You see either the particle nature, in which case you know its position, you know which hole it's going through, or you see the wave nature, in which case you know its velocity, you know how fast it's going. Okay? And that gives you an interference pattern. But you can't know both of those simultaneously. So notice what happens if you don't know the position and velocity simultaneously. Then you have what's called indeterminacy. Indeterminacy. What's indeterminacy? So remember last time we talked about determinism. The present determines the future. Indeterminacy is that the present does not determine the future. Okay? There's some randomness inherent in nature. Okay? If you did this double slit experiment over and over with the laser on, right? Sometimes you'd catch the particle over here, sometimes you'd catch it over here, even though you prepared the experiment exactly the same way every time. For any single electron, you can't predict whether it'll be here or here. But if you do the experiment over and over again, you can predict probabilities. All right? So what we're left with is the present does not determine future, right? So what you have instead are probabilities, a statistical description of what's going on. Okay, and we'll talk more about those probabilities in a minute. Lastly, from all of this, you can get the de Broglie wavelength of matter. These electrons, right, because they produce this interference pattern, they have a wavelength associated with them, all right? And that wavelength depends on their energy. So lambda is equal to h over mv, where m is the mass of the electron, v is its velocity, right? And h is just Planck's constant again. So, for example, if you wanted to calculate the wavelength of a particle, let's say a neutron, traveling at 100 meters per second, right? You have the velocity is that, the mass of a neutron is that, right? And you're trying to find the wavelength, and you're going to use this equation, right? So you're just going to plug in So first here, I'm just converting the mass to kilograms. Okay. And then I'm just going to plug into this equation. Lambda is equal to h over mv. So you put Planck's constant up here. There's the mass in kilograms. There's the velocity in meters per second, right? The kilograms cancel out. Meters squared cancel out. Second squared cancel out. And you get 3.96 times 10 to the minus 9 meters. So this is the wavelength associated with this particle, all right? And this equation helps you figure it out. Oh, you guys like this? Instead of working it out by hand? Huh. Okay.
It's clean with the crosses.
It's clean with the crosses, yeah. The mass has to be in kilograms, that's correct, all right? Because a joule has within it the unit of mass times velocity squared, all right? All right, so what does that mean? So for a particle, we have this concept of a trajectory, right? When the baseball player hits the ball, right? If you know the mass and velocity, you can figure out, boom, exactly where it's going to land, right? Through classical physics. So that doesn't exist for electrons, right? Because again, the particle nature is associated with the position, the wave nature is associated with velocity. You can't know both at once, so you can't know position and velocity at once. So what can we know? Well, this is a classical trajectory. In quantum mechanics, we don't have those. We have probability distribution maps, okay? Which means that for any single electron, you can't predict where it's going to land. But if you prepare many, many electrons in the same state and do the experiment over and over again and detect it, you can come up with a probability distribution of where you'll find the electron, okay? Another analogy would be a baseball player, right? A baseball player throwing a pitcher, throwing a baseball, boom. You know, you can know, the batter can watch it come in, right? Determine its mass and velocity sort of in their mind, right? And figure out exactly where it's going to cross the plate and put their bat right there to try to hit it, right? Go Dodgers. And however, for an electron, if you're throwing an electron across home plate, you could throw it in exactly the same way with no difference time after time again. And each time it'll land in a slightly different place, right? The batter would have no way for any single electron of predicting where it's going to be, all right? But if we observe many, many electrons, we can come up with a probability distribution map like this. So one electron would land here, one would land here, one would land there. And we could say, aha, 20% of the time the electron is going to be within that circle. 40% of the time it's going to be within that circle. 70% of the time it's going to be within that circle, right? So that's the kind of description we're going to have for electrons and atoms. It's not going to be an orbit because orbits are a trajectory, right? So those orbits that Bohr suggested could not exist for electrons, okay? What we're going to have instead is these probability distribution maps that tells us the probability of finding the electron someplace near the nucleus. Okay, good. Questions? I know Emily's question.
My question was already answered.
Okay, awesome. Any other questions on any of this? I know it's a little confusing. You have to like let it sink in a little bit to understand it, but I really want you to understand what an orbital is, because what we're going to see is that the orbits that were in the Bohr model get replaced by orbitals in the quantum mechanical model. And an orbital is just a three-dimensional probability map that tells us what the probability is of finding the electron in a particular place in space. Any other questions on any of this stuff?
Yeah, so is there technically electron could be anywhere, it's just the probability gets greater and greater in a certain area, but it can technically be like way out,
yeah,
you know, like way out there or some crazy thing like that.
The probability as you move far away from the nucleus drops to almost zero very quickly. But yes, technically you're right. There's some finite probability of it being found even far away.
That's crazy. Okay.
And undetected, it exists in all that space at the same time. Just like undetected in the double slit experiment, the electron is going through both slits, right? Where are we here? Undetected, it's going through both slits and producing this interference pattern. When you detect it, you localize it, you force it to be in one place. Just like when you detect an electron going through the double slit experiment with the laser, you force it to be a particle. So remember, the observation plays a role in the outcome of the experiment.
Okay. Okay.
I know it's hard to.
This is crazy.
Hard
That's
to grasp.
crazy.
It's a whole different world than the world we're used to, right? But that's the world of the electron. And this model explains things beautifully, including the organization of the periodic table, which we'll see in a minute. Not in a minute, but which we'll see next time. Okay, what else? Other questions? Okay, let me, if there are no other questions, I still got a few minutes. Let me introduce the fully quantum mechanical model of the atom. Okay, so in the Bohr model, right, you have a nucleus, has a plus charge, and you have orbits specified by a quantum number. Right? In the quantum mechanical model, this is for the hydrogen atom, right? So the electron in the hydrogen atom just sits here in the Bohr model in orbits around the nucleus like that. And energetic, you can give it energy and it can jump up to these higher energy orbitals, right? And then come back down. The quantum mechanical model, these orbits are replaced with orbitals. So these are orbits with one quantum number. In the quantum mechanical model, you have the nucleus, but then you have what are called orbitals, right? And these orbitals have 3 quantum numbers to specify them. Okay, not just one. You get these orbitals from solving a famous equation called the Schrodinger equation. And the Schrodinger equation, for those of you that have had differential equations, is just a differential equation that when you solve it, gives you something called the wave function. The wave function itself doesn't have a lot of physical meaning, but the wave function squared is proportional to the probability density of finding the electron. Okay, and I'll explain that more in a little bit. Okay, so solving the Schrodinger equation gives you the wave function and it gives you the energy. So just like hold on for a second. I've got hold on for a second. Hey, come past. Sorry, my son's out there making noise. So you get these wave. This symbol is called psi. It's the Greek letter psi. Okay, wave function and energies. All right, but the difference is that in the Bohr model you only have one quantum number. In the quantum mechanical model you have 3 quantum numbers. Okay, so what are those quantum numbers? They are the principal quantum number n, the angular momentum quantum number L, and the magnetic quantum number m sub L. So let me just find a little bit about these. So n is the principal quantum number. All right, n can be equal to 1, 2, 3, so and so on, okay? And n determines the energy of the orbital. So orbits in the Bohr model are replaced by orbitals in the quantum mechanical model, okay? Each orbital is specified by 3 quantum numbers instead of only 1 quantum number for an orbit in the Bohr model, okay? The first quantum number is the principal quantum number. It can equal to 1, 2, 3, and etc. And it determines the energy of the orbital. Okay, it determines the energy of the orbital. And the energy turns out for the hydrogen atom to be the same equation as the Bohr model, negative 2.18 times 10 to the minus 18 joules times 1 over n squared and equal 1, 2, 3, and so on. Okay. The second quantum number is L, which is the angular momentum quantum number. It determines, it can have values ranging from 0 up to n minus 1. 0, 1, 2, all the way up to n minus 1. All right. And it determines the shape of the orbital. All right, it determines the shape of the orbital. So the principal quantum number n determines the energy. L determines the shape. And each value of L is given a letter designation. All right, so 0 is given the letter designation S. 1 is given the letter designation P. 2, D, and 3 is given the letter designation F. Okay. And then lastly, M sub S is called the magnetic quantum number. And it determines the orientation in space of the orbital.
Don't you mean the spin quantum number is M of S?
Pardon me?
Isn't the spin quantum number M of S?
Yes, thank you. This should be M sub L. Thanks for correcting that. Determines the orientation of the orbital in space, okay? And so these 3 quantum numbers together specify an orbital. And then there's a 4th quantum number, M sub S, which is called the spin quantum number. Oh, and I forgot, I'm running out of time. We'll pick this up next time, but the magnetic quantum number can have values from negative L, integer values through 0 to positive L, okay? And the spin quantum number can only equal plus 1/2 or minus 1/2, all right? So those are the 4 quantum numbers. 3 of them determine an orbital, and we're a little rushed here at the end. Don't worry, we'll go over this again on next Monday. And then we'll see what these orbitals look like, right? And all will become clear. Okay? Any last minute questions before we stop? Okay. If there are no
Wait, can you
last
go
minute
back down to the spin quantum number?
Yeah, pardon me?
Can you go back down to the spin quantum number?
Yeah.
Yeah.
Okay, I'm going to stop the recording.